Oh,
coffee break.
sorry. Sorry. Sorry.
It's okay.
What is that time?
11, is it?
10:45.
Or is it 10:45?
No, it's morning. Oh,
So you
it
just wrote morning. That's the complaining. Two mistakes make it right. Yeah, make it right.
okay, yeah, now it is fine. It's not, I think. This is 5 minutes.
Shivashish, now everything is crashed. You're complaining aloud. I'm just joking.
Oh, good.
How are you? How's you doing? Just one.
You were not keeping too well.
I'm fine.
Okay.
Some shoulder, frozen shoulder.
Okay.
Because of temperature in Madras, things. I'm just joking.
Yeah.
Frozen shoulder. But I'm fine.
Okay.
I've been traveling. I'm
Yeah.
perimeter.
Yeah. I heard from Nandini and Mohit that you were spending time
So
there.
look forward to talk. And
Oh, well.
We'll be there today.
I'm here today and tomorrow also. Great. Nice to see you. Yeah. Hey, Surab, good to see you. Very well.
When did you come?
Yesterday evening. They told me that the following room was assigned to you, but someone took it.
No, come on.
This is a joke.
Oh, I see.
Hi, Anindya. Good to see you. Good to see you. So I know roughly what kinds of incendiary statements Surat's going to make, but I didn't have time to coordinate with you. So I just have a lead into you, but
Sure, don't worry. So you don't have any idea about what incendiary statements I'm going to
yeah,
make,
exactly. Yeah. Sorry.
Okay, welcome to the first session of the day. Our first speaker is Professor Sandeep Trivedi from TIFR, who is the former director of TIFR. He'll tell us about string theory, a quantum theory of gravity.
Thank you. Sure.
So this is for the people who are watching from YouTube. You are advised to write all your questions online, and then there will be somebody who will read those questions out loud in case they're there. Thank you.
Okay. Well, let me begin by thanking the organizers for inviting me to your great, wonderful celebration of quantum mechanics at 100 years of age. And it's really a great privilege for me to be here and to be speaking. My only worry, and I am filled with some trepidation on this count, is that I'm totally unequal to the task which was given to me by the organizers, namely to survey all of string theory. And this is a huge charge, and I told them that I was really not worthy of it. But since they persisted, here I am. And I apologize in advance to you for the many shortcomings in my presentation. But luckily, we have several experts from IMSC and from across the country here. So you will please correct me and improve this presentation as we go along even. The other thing is I won't be able to do justice to all the work, including work done by many of you here. So please excuse me, and it's in good part because of the limitations of time. Okay, so the title of my talk is String Theory, a Quantum Theory of Gravity. I thought I would emphasize the quantum aspects, particularly given the nature of this meeting. And what I want to tell you broadly today, so I thought, since attention spans are short, let me give the summary in the first 2 slides of my talk, then you can go to sleep. It's a 1 hour, 15-minute talk. So what I want to tell you broadly is that string theory is a very, I think, promising direction for formulating a quantum theory of gravity. It has had many remarkable successes, which I hope to bring out, some of which at least today. But important questions remain, in particular about whether string theory describes nature and how we can test it. Okay, and this I feel is the key question which remains. Of course, there are many more as we proceed in trying to understand string theory and its connections to the world around us. Okay, so we will survey some key aspects of string theory, what has been achieved and what remains to be done in this talk. Now, I'd like to start with some motivation. Why is an attempt at trying to formulate a quantum theory of gravity important and interesting? Then tell you in that broader context and in the context of some difficulties that have been encountered over the past several decades, why string theory is so attractive, why it has led to so much excitement, what are some of the key properties of this theory, and some of its key attractive features. So this is by way of a kind of introduction to the entire survey. And after that, we will move on to review some of the more exciting developments that have happened over the past, more recently over the past few decades. But even before embarking on the survey of string theory, let us ask from the point of view of understanding nature, as I said, why is it even important to formulate a quantum theory of gravity? A good reason in my mind comes from our attempts to understand the early universe. Extraordinary progress, as I'm sure you all know, over the past few decades in observational cosmology has taught us that the universe, very early on, let's say at the time of reheating, was remarkably homogeneous and isotropic, but also, and importantly, had small deviations from isotropy, for example. Understanding these very special initial conditions at or close to the Big Bang is one good motivation to try and understand quantum effects in gravity. These initial conditions, the small perturbations, for example, from isotropy are extremely important in the subsequent evolution of the universe. And our understanding today is that these small perturbations grew due to the attractive nature of gravity, giving rise to the large-scale, very non-homogeneous and isotropic structure we see in the universe today. So it's very important to understand the initial conditions because they really determine the universe today. Now, why do I say this is a question involving quantum gravity? Oh, well, just a little bit of data. Here is the beautiful CMB spectrum taken from the FIRAS experiment. You see how this is a black body curve, you all know. Can't tell experiment from theory apart. It's so good. Very precise measurements of the temperature. And this temperature agrees to a very good extent if you measure it in one direction or another. The deviations in temperature are only about 1 part in 10 to the 5. That's what I meant by saying it's very isotropic. But you do have these fluctuations measured now in many experiments in which India was a total non-participant. This is an issue we can discuss some other time. But anyway, these are among the greatest experiments done in the past few decades in the quest for a fundamental understanding of nature. So now, why do I say it pertains to quantum mechanics? Well, the leading theoretical explanation, I would say, for these initial conditions is that the universe went through an epoch of very rapid expansion in its early history called inflation. Quantum fluctuations during this epoch gave rise to the small anisotropies. So if you want to understand them, you need to understand quantum fluctuations. And here are the perturbations characterized. They are Gaussian to good extent with small deviations, we think, not observed yet. But this is the 2-point correlator, sorry, there should be a bracket closing here, in the metric perturbations not observed yet. And this is what is observed. These are scalar perturbations, never mind those technicalities. The important thing is the perturbations go like g Newton times h bar, okay, in c equals to 1's units. I've set the speed of light equal to 1. So they require you to understand quantum gravity, okay, h bar and g Newton effects when they come together. So this in my mind is a good motivation. Another motivation comes from the current status of our understanding of the fundamental laws of nature. These, as you know, are summarized in the Standard Model, which is a remarkably successful theory, but it's got 19 fundamental constants, okay? And this point. So, here, for example, if you take the mass of the top, it agrees very well between the experimental value and the Standard Model and so on. You can go down. So it's a very successful theory. But it's got all these constants, many particles, 3 generations, several forces, and to paraphrase, who was it, Rabi, I guess, you can say, who ordered this particle content? Where does this zoo of particles comes from? Who ordered these 19 fundamental constants? Could they have taken very different values? Could you have had even more interactions besides the strong, weak, and electromagnetic ones, or less, etc.? Those kinds of questions are naturally prompted by the current understanding we have of the Standard Model. And the hope, and this has been a hope for a very long time in the field of particle physics, etc., is that combining gravity with the other fundamental forces of nature in a unified description based on quantum mechanics could lead to a unified theory with no or maybe few parameters. Okay, so this is the hope of unification. This is prompted by our current understanding, which leaves us dissatisfied. Makes one think that there's something more. And so the hope is, currently we do understand the workings of electromagnetism, the weak and strong force based on quantum mechanics, not gravity, but the hope is perhaps if on the basis of quantum mechanics we understand all the fundamental forces, then that will lead to tighter theoretical restrictions which might also remove some of the seeming freedom we have and see in the Standard Model. So this is another motivation coming from, from just what we know about, this pointer has given way, but luckily, okay, so now on to trying to understand a little bit more about string theory. Now, in the early days when people tried to construct a quantum theory of gravity, they ran into this rather famous problem of renormalizability, and it proved to be a big stumbling block. The fundamental reason why this problem is so acute in gravity is that the coupling constant of gravity, which involves G Newton, is a dimension full, is actually the correct coupling constant is inverse of this. So you should think of it as, because h bar comes on top, this pointer is given way. You should think of as m Planck square, which is h bar c over G Newton, and this has dimensions of mass square, and that means the perturbation theory, one does, involves energy square over m Planck square. That is the dimensionless parameter, or in other words, G Newton h bar c times E square, and this coupling constant, this dimensionless coupling constant grows with energy. Okay. In electromagnetism, in contrast, the corresponding coupling constant is a fine structure constant. It is dimensionless, at least as per naive power counting. Then it has a kind of slow growth with energy, but it's logarithmic. Here and we know how to deal with that, more or less. But here it's much more severe. It's a power law divergence. And this is the root cause of renormalizability problems in gravity. This Planck scale, by the way, is a huge energy scale, about 10 to the 19 GeV. And since it appears in the denominator here, that means the corrections might be small if you are just looking at them at low energies, but they will grow as you go to higher and higher energies. Now, so here I'll show you what I mean by the problem of renormalizability a little in more detail. As you know, one can compute in perturbation theory the effects of various interactions by calculating Feynman diagrams. And this diagram here has a graviton which is being exchanged between, say, two particles, could be electrons, could be protons, or whatever. And this exchange would give rise to the classical Newtonian force. and m Planck square comes in the denominator, which means g Newton comes upstairs, which of course is what we know because the force goes like g Newton m1 m2 over r square. But now in the quantum theory, you have loop effects. And since you have 4 vertices, when you calculate, that means you need a power of m Planck to the 4. Each vertex has a 1 over m Planck. And dimensionally, here I've taken out an overall factor, so the leading term is dimensionless, so any correction also with that normalization would be dimensionless. So since you have m Planck to the 4, the remaining contribution due to the loop has to also have dimension 4, and turns out to be an integral over energies running in this loop of this form. And it goes, if there was an upper cutoff of some E max, it would go like E max to the 4th power. If the theory of gravity was all that there was to it, Einsteinian gravity was all that there was to it, this would go all the way up to infinity, and this would diverge. Okay, and so from the fact that the coupling constant has these dimensions of m Planck square, has dimensions of mass square, it follows that quantum effects, okay, even if external energies are small, quantum effects would lead to divergences and infinities. And this was a huge problem in the study of gravity and a real stumbling block. In contrast, and this was one of the reasons for great excitement early on in the field, string theory, which is a theory of based on quantum mechanics, contains gravitons, which are massless spin 2 excitations. It contains those degrees of freedom of gravity. These UV divergences, high energy divergences, are absent. And what happens is that one way to understand this from the point of view of effective field theory is that this integral gets cut off in terms of just the contributions from gravity, because other degrees of freedom start coming in as you go to very high energies. Other string excitations start coming in. But a much better way physically to understand what happens is that strings are not point-like, they have an intrinsic size, which I'm trying to show here, and they are therefore floppy objects at some scale, the string scale. So when you hit that scale, what happens is these UV divergences start getting softened out, and they no longer grow in this way that I was telling you about. And it's of course true also at the tree level that you have extra degrees of freedom, but certainly when you go to loops, the fact that strings are floppy, that causes the change from being divergent to a finite contribution. And this is a very fundamental property of strings. It arises from just the fact that you have an intrinsic cutoff on size once you're dealing with extended objects. Sharp interaction vertices in quantum field theory are also smoothened out. The nature of the excitations are smoother, and that all results in a much better ultraviolet behavior of the theory. So this is in fact we now know this is a universally true feature, regardless of which interaction. I showed you a 4-point interaction, but it's universally true that there are no ultraviolet divergences in string theory. Okay, so it is a candidate for a ultraviolet complete theory, okay, of quantum gravity. And corrections to leading tree level processes can be calculated in a systematic manner in perturbation theory, like you would compute corrections to, G minus 2 or your favorite quantity in electromagnetism, or the strong interactions. In the strong interactions, if you're at high enough energies, calculate them systematically. You can do the same thing here in string theory for processes involving graviton exchange or quantum effects involving gravity. Okay, so that's a remarkable thing about the theory. And it solves the problem of renormalization in quantum gravity, which has really bedeviled all efforts in the field for a long time. Now some other key properties of string theory. I told you they are extended objects with a scale which we call the string scale. We don't know exactly what that scale is, by the way, if string theory were to pertain to the real world. And this is an example of the kind of questions we don't know answers to today. But there is a scale for sure which will cut off that growth at very high energies. And that's enough to show that it's a renormalizable theory. You can have two kinds of strings. There are open strings which have endpoints, and there are closed strings which don't have endpoints. So here is a set of figures, closed strings and open strings, and these strings can vibrate in many different modes shown here, and these different modes of vibration of the strings then give rise to the different kinds of particles in string theory. So one kind of excitation of the closed string is the massless spin 2 particle, the graviton. Other excitations could be heavier states. Some excitations of closed or open strings could be the kind of particle content we see in the standard model. That is the hope. And these different excitations then can be particles of different masses, spins, charges, and so on. The fact that these different excitations of the same underlying string, the fact that these different excitations are those of the same underlying string, holds out the hope that their interactions have a unified or common description, because they're really all described by just one kind of string in the end, just vibrating and interacting in different ways. So the hope of grand unification was something also that seemed sort of natural, that string theory would be a natural setting in which we could hope to try and fulfill this. So this was another reason for the great excitement in the subject. The theory preserves Lorentz invariance. It's consistent with special relativity, of course consistent, as I said, with quantum mechanics. It has supersymmetry, which is a novel kind of symmetry in its fundamental formulation, a novel kind of symmetry which relates bosons and fermions. And in general, these properties give it a very tight theoretical structure, okay, in its fundamental formulation, very little leeway. And for example, one of the consequences is that string theory requires 10 dimensions, 9 dimensions of space, and 1 of time for its formulation. Okay, you can't mess with that. Of course, I'm simplifying things somewhat. Sometimes the extra degrees which come with the higher dimensions may not have a geometrical description, but let's say here that it requires 9 dimensions of space and 1 time, and you can't mess with that. It's part of the theoretical, the tight theoretical structure. How can this connect with the real world, which has 3 space dimensions? We'll come to later on in the talk. It has no coupling constants. It turns out. The only scale is the string scale, but that's a dimension full scale. You can measure everything in those units, and then there are no dimensionless coupling constants in the theory. The coupling constants of the standard model are expected to arise as expectation values of dynamical fields. Okay, so for example, there could be a field which is dynamical. It takes a certain value which gives rise to the fine structure constant having the value it does in nature. That's how the theory is set up. However, it turns out that there are a lot of possible values, expectation values, sorry. There are a lot of possible expectation values these dynamical fields can take. Sorry about this. And that contributes to the kind of choice we get when we try to solve the equations of string theory. And more on this later as we go along in the talk. So ultimately it turns out that string theory does give rise to a diversity of choice in terms of a low energy description, but at least in its fundamental formulation it has no arbitrary coupling constants in it. And that makes it an attractive starting point. When string theory came on the scene, a central question was, can a quantum theory of gravity be formulated at all in a mathematically consistent manner? Or are there irreconcilable differences between quantum mechanics and gravity which prevent such a theory from existing? Okay, this was a key question because it had proved so difficult till then to formulate a quantum theory of gravity. And I emphasized the problem of renormalization earlier and how string theory solves that problem and deals with it. But there was another reason to be worried about a great deal of tension between quantum mechanics and gravity. And this came from what had been learned about the quantum behavior of black holes. As Hawking especially emphasized the behavior of black holes, the fact that they had a temperature, etc., suggested that perhaps information was lost, that perhaps the process of forming a black hole and its subsequent evolution was not describable as unitary time evolution of the kind that would happen in quantum mechanics. And if that were indeed the case, then gravity could not be reconciled with quantum mechanics. So there was another reason coming from really studying gravity very different, in a very different regime from that of perturbation theory, of one graviton or two gravitons, etc., being exchanged. Here we were dealing with intense gravitational fields of the kind we have in black holes. Again, questions arising about whether we could reconcile the behavior of gravity with quantum mechanics. Progress over the past few decades leaves little doubt in my mind that string theory is a quantum mechanically consistent theory of gravity. We'll review some of this progress in the context of what has been learned about black holes and their quantum properties in string theory. And it's very impressive and spectacular progress. And I think there's very little doubt that we have a quantum mechanically consistent theory. And this, in my mind, is the central advance. Okay, we now have an answer to the question, can you have a quantum mechanical theory of gravity? And the answer is yes, and string theory is the existence proof. Okay, I think, there's very little doubt that there is a consistent theory of quantum gravity in which string theory describes. As I said, that doesn't mean the story is over, but in fact many questions remain, and the key question is, does it really describe the real world? So we'll come to that. So now,
So the thing about the coupling is that it does not have any coupling. The tube picture you showed, is there one input that the probability of a string splitting, is that an input, or is it?
Well, you can have string, if you just write down the dynamics of strings, they can split and so on, but it's not as if you have a tunable coupling constant that you can put in. I mean, what you do have is a coupling constant of sorts, but it should be thought of, let's say the string coupling constant, but it should really be thought of as the expectation value of some field.
Okay.
And so the idea is that you have some background which solves the equations of motion, say, of string theory, and in that, if you're doing perturbation theory and computing, say, Newton's law, then you would put in the expectation value of some
Which would be an input.
Which would be an input then,
Okay.
but determined by the background. So that is the sense in which you do have an input, but it's not a fundamental constant that you can dial.
I see. And the connection between the string scale and the gravity scale, can they be very, can they be separated a lot, or are they close by, always necessary?
Yeah, no, so that's the kind of question we don't have an answer to. How far would they have to be separated? And when you work it out, that ratio of the Planck scale is higher than the string scale, that much you can see. But the ratio of the Planck scale to the string scale involves the expectation values of some of these fields. In particular, there's a field called the dilaton which goes into the string coupling, and the volume of the extra dimensions. These two are independent parameters, and both of them go into that relation. We don't know what values those take today, so we can't answer this question.
At least as a possibility, you can just input very different scales.
As a possibility, you can do that, and there are compactifications with a lot of supersymmetry where you can in fact argue that these expectation values can be continuously varied also, and then you can just take the value you want and investigate the theory.
Have any dynamical example of such a separation, properly demonstrated, as an example?
Right. So what we would want is an example where these expectation values are fixed and they take very different values. And we'll come to some of that towards the end of the talk, but the short answer is that, we could try to construct examples like this, and indeed they can be constructed, but and my own work has been in this direction, but the ones we know with the greatest confidence are examples which have a lot of supersymmetry in them. Whereas, perhaps what you might be more interested in are examples without. And there we have less control today. But with supersymmetry, we can have a huge hierarchy of scales, and those compactifications
But if
are
we
known.
put in the known ideas of supersymmetry breaking, can they be made more realistic or?
I'll come to that. I'll come to that, at least to some extent.
Sandeep, I have a very stupid question to ask. You talked about these particles being excitations of the string. But is there anything that one can even conceptually think of? Maybe it won't be practically possible, but can one try to understand what is the string? Or it can only be looked at through the excitations of that string?
Yeah.
Is it a stupid, I mean, it's probably a
No,
stupid question, but
Yeah, I don't know how to answer that. I mean, yeah, the string theory gives rise to a spectrum. So you can look at the spectrum, it gives rise to interactions. But
no, the analogy would be, let's say you have a nucleus who can be excited, atom which can be excited. And of course, you can understand a lot through its excitation spectrum and through its properties. But you would like to know whether the atom is really there or not, and you would like to probe that. So in that, as I said,
okay,
I don't know whether
I'm
it
not
can
sure
be there
other
or
than,
not, but-
yeah. I'm not really sure. Maybe you can talk about it a little more. What kind of experiment you have in mind that would convince you a nucleus is really there rather than scattering things off it, and then we can see if there's a corresponding parallel here. Okay, so let me go on. I'm running a little behind, but it's good to have done the introduction slowly. So the rest of the talk, what I want to tell you about is the progress made over the past few decades on understanding the quantum properties of black holes in considerable depth, in string theory, and the related idea of holography, which we have learnt about, which is really quite remarkable. Then this Surat I think we'll talk more about, and I'll be brief about this, but it really does deserve a place in any general survey. Then I'll tell you about the attempts at unification within string theory, how far we've been able to go, the challenges, etc., which are raised when we try to connect string theory with the real world. Dark energy, try to account for dark energy. It should have been the cosmological constant, but actually it's good, it's S, because we get varying values and a picture of a landscape of many possibilities. And then end with what is perhaps not the central theme as I am projecting it today, but anyway very important developments which connect string theory to other branches of science and mathematics. I think Anindya will talk more about the connections with mathematics later on today. So that's the overview of the talk. Okay, let's see, this pointer is, okay, black holes and holography. As I mentioned already, the gravitational force is very strong in a black hole, so strong that not even light can escape its gravitational pull. So if you're trying to understand, effects, quantum effects, etc., generally intense gravitational effects, black holes are a very good setting. And in fact, you will see, trying to account for the quantum behavior of black holes and its properties requires us to understand gravitational effects in a non-perturbative manner. When we were trying to do graviton exchange and so on, the corrections went like h bar, the one loop effect went like h bar compared to the tree level effect. But here the kind of properties, the entropy for example, will go like 1 over h bar. So it's really a non-perturbative property of the black hole, and we will try to account for it in string theory. Okay, now starting from Bekenstein and then Hawking, as I mentioned, a lot was learned about the behavior of black holes in a semi-classical kind of context, and what was learned was quite remarkable, that black holes behave like other kinds of thermodynamic systems. They have a temperature, they have an energy which you can think of as mass. I've set the speed of light equal to 1, and they have an entropy. And furthermore, these parameters which are tied to the behavior of their horizons satisfy the laws of thermodynamics. So for example, T ds equals dm minus omega dj, j is a charge, the angular momentum, and so on. So that was a remarkable set of developments, and out of Hawking's work came a precise temperature which went like h bar. It was a quantum effect involving gravity, the black hole's mass and Planck's constant in units C and KB equal to 1, and an entropy, and the entropy formula is very interesting. It goes like the area of the black hole horizon with in units of h bar times g Newton. When you do dimensional analysis, you can put these in, and so h bar comes in the denominator. Okay, and that's the sense in which the entropy is non-perturbative. Okay, and so the question which arose was, from the time of Boltzmann, we have learned in usual systems in physics that entropy can be explained in terms of the number of available states. Entropy equals, here I put back in KB, Boltzmann's constant times log omega. Omega is the number of available states a system has. If you're at some temperature, you have access to some number of states. Entropy is up to this constant log of that number, and so on. And the question was, can we understand the entropy of a black hole in the same way, in terms of statistical mechanics, in terms of degrees of freedom making up the black hole, count the number of such states those degrees of freedom can be in, and get the entropy as log of that total number. Okay, and this would be something which would be a non-perturbative test. It would account for the entropy going like area over h bar g Newton in the gravitational setup. So this was a major question, and one of the great successes of string theory in the past few decades is that it has been possible to do the counting and to get an answer which agrees with the Bekenstein-Hawking answer, and to get it to agree, as I'll show you, with a very high degree of precision. There are corrections to the Bekenstein-Hawking formula, which I'll tell you about, which arise in string theory. They can be calculated on the gravitational side, and they agree with the corrections which arise when you try to just count the number of states. So it's a very beautiful, very, very precise connection, which leaves no doubt that for the kinds of black holes where it's been possible to do this, the two descriptions are in complete agreement. And string theory, with its degrees of freedom, its strings and so on, really does correctly account for the degrees of freedom in a black hole. Okay, and so this is a huge non-perturbative test for string theory as well. Many people have contributed. I'm sorry, I'm not going to be able to do justice. Ashok wrote actually one of the key seminal papers, really remarkable paper, Strominger and Vafa. After that, Maldacena, Dabolkar, Murthy, and then in terms of string models, which in some sense got the essential physics, but these of course are very, very precise. Beautiful work by Dhar, Mandal, Wadia, Das, and Mathur, etc. Only an incomplete list, many Indians, so I really do want to mention this. And the key idea in the precise counting, etc., which is done is the following. For now, let's start with the supersymmetric black hole, but after that we'll go on to non-supersymmetric ones as the talk progresses. For supersymmetric black holes, you count the states at weak coupling when gravitational back reaction is small. So that's easy. You look at how the black hole is described in string theory. It's some collection of strings, maybe other objects like membranes or their generalizations, which we call D-branes. And in terms of weakly coupled string theory, you count how many degrees of freedom there are. This coupling, which is really the expectation value of the dilaton, is taken to be very much smaller than 1, so this count is easy to do. You get an answer. At this stage, the system is not a black hole because its intrinsic size, partly because it's made out of strings, partly because of the Compton wavelength of the system, is bigger than the gravitational radius. But now you crank up this coupling, because let's say you're working in a class of string theories where this expectation value can be continuously varied. You crank up the coupling and increase it till gravitational effects become big, and then the system turns into a black hole, and at that point you calculate the Bekenstein-Hawking entropy, the area of the system, a horizon of the resulting black hole. And you find that the number of states you got when you did the microscopic count at weak coupling agrees with the Bekenstein-Hawking entropy to very, very high precision, as I said. This is the chain of argumentation, okay, which was carried out. And we'll come back to some of the caveats in a minute, because they've been much better understood. But just to give you an example, let's start in 5 dimensions. Of course, our real world is in 4 dimensions. You can do this for classes of black holes in 4 dimensions as well, but let's start in 5 dimensions. That's where it was done first. You have a system which has 3 kinds of charges, and you're looking at what are called extremal black holes, which are also supersymmetric. So they have the lowest energy given this charge. So they're like ground states in this charge sector. And these are all integers in appropriate units, and microscopically you know how the system is built up with strings, etc. You now count the total number of states, and the result you get from that microscopic counting in string theory is a nice formula like this: square root of q1 q5p with this prefactor, and then you go ahead and you compute the area of the system when it turns into a black hole, find its area, etc., and compute the same quantity, and you get an exact match. Okay, very precise match. So this is one small example, but it's been now done in many contexts, and you get this agreement. Now there's a very important assumption I'm making, which is we're assuming that the number of states does not change as you go from weak coupling to strong coupling. You know, I said you do the counting when this, what I was calling coupling G string, is small, system is not yet a black hole, then you crank it up, you go to the other limit where it becomes a black hole. You could ask, well, how do you know that the number of states doesn't change? You know, even if you're talking about states which are the lowest energy states, it's like the ground states. States which are at low energy can, you know, become at higher energy as you change coupling constants and so on. So why should the two have even agreed? Why is this even a test? And the technical answer is that what we compute microscopically is not quite the total number. The total number of states would be number of bosonic states plus fermionic states. What we actually compute is the index, the number of bosonic states minus the number of fermionic states. And you can argue that the index is actually protected in going from weak to strong coupling. Okay, this is a bit technical, but I want to mention this for completeness. And the reason is all let me call the lowest energy state the zero energy state. All the non-zero energy states have to be paired up between bosons and fermions, so equal numbers, they can't contribute to the index. So if you start with the index taking some value, say at weak coupling, and as you go to strong coupling, some states which were at zero energy get heavy, they all get heavy in pairs, so the index must be preserved. Okay, so the kind of argument I gave you saying that you compute something at weak coupling, it will, and you can compare it at strong coupling and check whether you get agreement. This argument is really in solid footing if you apply it to the index, not to the total number. But of course, the Bekenstein-Hawking entropy gives us the total number. It comes from thermodynamics. Thermodynamics cares about log of the total number of states, right? So why should the two agree? And this was a bit of a puzzle, and there was a sort of heuristic understanding that you go to strong coupling, everything that can pair up pairs up, so what you're left with is only bosonic states. So then the total number, if the final number of fermions is 0, total number will be just NB, index will equal number of states if you have no fermions. This was the heuristic understanding, but it was too heuristic. It has been much improved now, and for example, it can be rigorously argued that in some cases when you go to the gravitational description, because of the symmetries, the supersymmetries, etc. involved, the fact that you're in 4 dimensions and supersymmetric states cannot be rotating black holes, etc. You can very rigorously argue that in fact what I said, the heuristic argument is correct. By the time you go to the black hole description, all the states are bosonic. Therefore, the index is really equal to the Bekenstein-Hawking entropy. So you can say, here's the test, we compute the index at weak coupling, and that should remain the same, and that should become the Bekenstein-Hawking entropy. Therefore, it should agree with area over 4g Newton h bar, and indeed, look, we compute the index microscopically, and it agrees bang on. Okay, so it's a very rigorous test now. It could have failed easily, and it doesn't in many cases. So that's the status now. The counting has been extended. As I said, the result I stated to you, square root q1 q5p, was the leading answer in Einstein gravity. Root gr Einstein gravity, but string theory has corrections to Einstein's gravity. And so you can ask, okay, on the gravitational side, let me compute the corrections. On the microscopic side, let me compute the corrections. Do they agree or not? And this has been done to exquisite precision. The mathematics is really beautiful. I don't know if Anindya will talk about it, because you're counting, all kinds of beautiful ideas in number theory come in, involving cusp forms of various types, Mach modular forms. This is Ramanujan Auditorium, one has to mention, and so on. Beautiful ideas, and they on the gravitational side also you have to extend the description. This requires us to understand. Where did it go? Sorry. On the gravitational side, it requires us to extend the idea of the Bekenstein-Hawking entropy to include higher derivatives due to Wald, and this includes what are called a class of string theory corrections, but then a further generalization due to Ashok based on the quantum entropy function, which allows you to compute quantum effects. So, it's really exquisite checks, higher derivative checks, quantum corrections and so on, and they end up agreeing in some cases. You get beautiful expressions, very intricate as functions of charge on the microscopic side, on the gravitational side, and they agree. Okay? Reproducing beautifully the gravitational side, which also comes from string theory with its various corrections, because the string has a finite size and so on, beautifully reproduce the results coming from black holes. So this is a very non-trivial check. Yeah.
Why is the number of states?
The number of states is finite because you're counting just the ground states in a particular charge sector.
Okay.
And so, you can say, okay, let me just count the number of ground states. That will usually be finite. Of course, the tower of excited states will be, go on forever, but we limit ourselves to that sector, and that's finite.
Is that to be thought of as some eigenvalue equation kind of thing, and you count the eigenvalues, or is that different?
Yeah, you can think of it as the eigenvalue for the energy given the charges the system carries. Okay, so this is a very impressive test, and it's been extended to been extended to non-supersymmetric settings, and is found to be true in classes of non-supersymmetric black holes as well. And I'll give you an example of this. You might say, this is all very well, this is some supersymmetric system, this and that. No, I'm interested in a quote-unquote real-world black hole. None of this supersymmetry, just at finite temperature and so on. Now, I can't give you an agreement with real-world black hole because we don't know how to find the real world in string theory today, but in a much more realistic black hole at just finite temperature, a remarkable agreement which I'll show you about. So this has been extended, much beyond these settings where already it's tested very exquisitely. Okay, so it's a highly non-trivial check. Okay, now let me briefly talk about holography. Now it turns out, as I showed you, the entropy of a black hole is proportional to its area, and I didn't say it then, but actually this is a very, very strange result, because for all other systems, entropy is an extensive quantity, right? And what that means is, if I take gas at some temperature in volume V1, same temperature in volume V2, I put the two together, well, nothing, the properties are the same temperature and so on, so the system is automatically in equilibrium, and I compute the entropy. What is the entropy of the system when it has volume V? Well, it's the entropy of the V1 plus the entropy of the V2 systems. Okay, entropy is additive. Okay, and that means it scales like the volume. Okay, this is a very basic thermodynamic property, but of course, as I said, for a black hole, the entropy goes like the area, which means if you think of the black hole enclosing some region of space of radius r, the entropy doesn't go like, say, 4 over 3 pi r cube, or doesn't scale even like r cube. It instead goes like r square. And that's a much smaller number of degrees of freedom than had it gone like r cube. So this is a very, very funny feature, very strange feature that comes out from black holes, that the entropy goes like the area. And this is the fundamental bound on how much entropy you can have in some region, because if you take some region and start packing stuff into it, ultimately, initially you might have some dilute gas or something, but as you start stuffing more and more of the gas, eventually it will collapse to form a black hole. And when it collapses to form the black hole, the entropy goes like the area. While you're stuffing stuff in, the entropy is going up. Eventually it saturates at something going like the area. So it's the area which provides the maximum bound on the amount of entropy you can contain in some region. Very, very, very unusual behavior, but true in gravitational systems. I haven't used anything about string theory here really, just coming out of the work of Hawking and Bekenstein and analyzing gravity in the semi-classical approximation, that is to say, without the intricacies of string theory, etc. Okay? So this was general feature, but any consistent theory, quantum mechanically consistent theory, should be able to account for holography. Very strange behavior should be able to contain that feature in it. In fact, Toft and Susskind suggested that this is a fundamental feature of all gravitational systems, that in fact the true number of degrees of freedom in such a system should be much smaller, as I said, and be in scale like the area, that is, the true number of degrees of freedom of such a system should be thought of as living in, or should be thought of as allowing for a description in one lower dimension. Okay, so this was the general thinking. Here's a hologram, and they coined this word that the world is that gravitational system should allow for a holographic description in one lower dimension, just as holograms can encode because of interference and so on, three-dimensional images. I put this up also, which some of you might have seen at India Gate nowadays, used to be, I think no longer. And the idea is that the world is a kind of hologram like this. It's a gravitational system, looks like we are in three space dimensions, but the fundamental count suggests that maybe we are in one lower dimension. Now, in the context of string theory, is this true? And in fact, it was shown in a remarkable set of developments that in fact the idea of holography is borne out in a very precise manner in string theory. In some contexts, you can take string theory in space-times which are called anti-de Sitter space-times, where the cosmological constant is negative, and in those cases, starting from the work of Maldacena and onward, we could argue in a very concrete way that string theory admitted a hologram, a very precise description in terms of a theory which was living in one lower dimension. And so here's a famous example. Take a particular kind of string theory, 2B string theory, in a particular anti-de Sitter space, ADS5, five-dimensional anti-de Sitter space. There's an extra compact sphere. That's not so important at the moment for our discussion. And the claim was that this is equivalent, is dual, which means equivalent with some properties, to a close cousin of the strong interactions. A Yang-Mills theory, like the strong interactions, as you know, are also described by Yang-Mills theory. So here also we have a Yang-Mills theory, a non-abelian gauge theory with some supersymmetry. And the Yang-Mills theory, which you can think of loosely as living on the boundary of ADS space, say here, is in 3 space and 1 time dimensions, and anti-de Sitter space is in 5 dimensions. So you have one dimension which is being reduced, as one might have thought, on general grounds from holography. So this was the proposal. It came out of a very intricate argument using the various gears and wheels of string theory, but was a very concrete proposal, caused a lot of excitement, and one of the reasons it caused a lot of excitement is that the hologram, the lower dimensional description, is a much more ordinary object. It's a close cousin of, as I said, of the strong interactions. It has none of the mysteries of gravity. It's definitely quantum mechanical. We believe it can be, rigorously, it can be well defined, etc. And if that is equivalent to all of string theory with all its mysteries and gravity and so on, well then that's quite remarkable, you know. And the nature of this equivalence is a duality, which means the gravity side is strongly coupled, the Yang-Mills side is weakly coupled, and this, when the Yang coupled, then the gravity side is weakly coupled. So there's no free lunch if you want to understand, you know, weakly coupled gravity. In our world, gravity is weakly coupled, right? The gravitational force is weak. Then you have to do some hard calculations on the Yang-Mills side, but okay, you know, you do the hard calculations. The hope is you can then describe gravity in this large, smooth background. So this caused a lot of excitement, and the chain of argumentation was embedded into the internal logic of string theory, and it's been subjected to a lot of checks. And one set of checks comes by studying the spectrum of excitations, supersymmetric excitations on the string theory or gravitational side and on the Yang-Mills side, and finding that they agree very well in this ADS5 example, and many other examples of this type in 4 dimensions and so on as well, and computing some correlation functions which are also protected, so you can again compute them at weak coupling, let's say on the Yang-Mills side, and then argue that they should not change, and then compare them with the gravitational description where you are at strong coupling. Okay, so these kinds of supersymmetric checks, and they've all been shown to be borne out. Now, interestingly, there are checks which are very far away from supersymmetry, which don't use supersymmetry, and I want to tell you about one of those checks, which is really quite remarkable. But before I do that, let me go to the central point here, which is that you know, the beautiful checks which have been carried out leave really little doubt in anyone's mind that these holographic correspondences which have been discussed today and related ones are actually correct. And we can now turn this around to provide a non-perturbative definition of string theory, okay, by saying, look, if it's equivalent to a Yang-Mills theory, and Yang-Mills theories we can define in a precise way, going back to the work of Wilson and so on, in a very precise non-perturbative way, then that becomes the non-perturbative definition for string theory. And the description in terms of Yang-Mills theory is certainly based on quantum mechanics. So in these kinds of backgrounds, we now have, thanks to this holographic correspondence, a very precise non-perturbative definition and description of quantum gravity based on string theory. Okay, and this is quite a major advance given where we started, where we weren't even sure whether black holes, their behavior could be reconciled with that of gravity, of quantum gravity. But now to go back to this check, which I really want to tell you about, there's a version, I told you that, you know, here in the version I was describing it, some Yang-Mills theory in 3 + 1 dimensions and all, but there's a version of this Maldacena correspondence which is conceptually even simpler. And there, instead of a 3 + 1 dimensional field theory, you just have quantum mechanics. You have a bunch of matrices, okay, which you can just think of as a bunch of particles, okay, with some potential moving around. And here is the Lagrangian. There's some gauge field, but you're only in time, so the gauge field is a constraint, not propagating. You have n by n matrices. Think of them as just, you know, point particles, or, you know, just moving in time. 9 of them, some fermionic degrees of freedom. Think of them as spins. Okay, very conceptually, very simple situation, setting or model. Okay, and in this model, the correspondence says, go ahead and compute the partition function at finite temperature. This is like conceptually a very garden variety calculation anyone in statistical mechanics will do. Okay, your quantum mechanics, some combination of harmonic and harmonic oscillators, put them at finite temperature, compute the entropy. Okay, compute it, and it will agree with the entropy of a black hole calculated using the mysterious formula of Bekenstein and Hawking. Okay, when you go to the correct limit, so you can compare apples with apples, okay, it will agree with this. Now, this is a remarkable thing, okay? We have stripped down holography to a very simple conceptual setting. And this test was carried out, and I want to show you the data. It's really beautiful. It's numerical. When you go away from supersymmetry and so on, you have to do numerics, you have to do hard work. But it's been done, beautiful work by Hanada and his group and various collaborators. And let me walk you through this transparency a little bit. The blue line is the result you get for the Bekenstein-Hawking entropy using Einstein's theory of gravity, okay? It goes like the temperature to some power. This is an odd looking power. You said here I've got energy in some units. Well, how can energy go like temperature to some crazy power? There's a coupling constant in the game which I've set equal to 1. So this is in units of that coupling constant. String theory has no coupling constant, but that coupling constant is made out of the string scale, okay? So which is dimensionful. So never mind all that. It goes like t to the 14/5 with a precise coefficient that comes out of Einstein's theory in this setting, and this is that curve. Now, the orange curve is what comes out of string theory. It agrees with Einstein gravity when you go to low temperatures. At higher temperatures, it turns out the corrections, okay, the geometry starts deviating from being very smooth. So, gravity is a good approximation here. The string corrections get important as you go further and further. In string theory, you can compute the powers you get for the corrections. They go like these peculiar powers, but you can compute them, what they are. Here is the numerical data plotted. There were 2 runs because it's very computationally expensive, plotted here in purple and here in red. And the first thing that hits one is that, look, the 2 results converge, okay? The numerical results converge with the gravity answer, okay, as you go to low temperatures, okay? My God, okay. As you go to low temperatures, okay? Which means you are computing from this matrix theory the Bekenstein-Hawking entropy, okay, and getting agreement. How good an agreement do you get with 7.41? Okay, you get the value you extract numerically is 7.4 plus minus 0.5. 7% error. Okay, you land on the Bekenstein-Hawking entropy. Furthermore, you see, the numerics agrees with the string theory corrections very well. Very well. You can even subject it to further checks and say, can I even check these powers? Okay, can I check these powers? And you can do that. You say, okay, well, the numerics isn't good enough to totally check the powers. You say, okay, I'll just allow the powers to vary by, they vary by a 6/5. You can show in this power series. Take this one to float, and again you get an agreement with string theory to within 5 or 7%. Okay, so it's really beautiful checks, okay? Now completely non-supersymmetric, not using any special features, getting the Bekenstein-Hawking entropy right. This leaves, I think, very little doubt that holography is correctly implemented in string theory, that string theory admits this kind of a non-perturbative description in terms of quantum theories in one lower dimension. Very conceptually much simpler quantum systems. Okay, so now I really have to move on. And I will do that. I think we'll hear more about holography in the next talk. Let me now move to attempts at unification. Now, at first, it seemed that within string theory itself, there were a few different kinds of string theories. I'll just spout out the words: 2A, 2B, 1, SO32, E8, a few of them, M theory. And well, that seemed a bit disappointing if you were hoping to unify everything, if the starting point itself had at least some discrete amount of choice. But then subsequent work found that in fact these are different corners of the same underlying theory, revealed just different limits of the same theory. And so there's some underlying theoretical structure. You go off in some limit, varying some of the expectation values of some of the fields. They land at one end, other end, and so on and so forth. And in that way, all string theories are actually, unified in terms of the same underlying theoretical framework. What about the extra dimensions which are present in string theory? Well, the idea was that going back to the work of Kaluza and Klein, you could make the extra dimensions small, and that way evade their detection. So if you have a fat cylinder, you can of course see that you have the length but also the circle, but if you make the circle much smaller than the length, then maybe you can't see it with finite resolution of any probe. So this was the whole idea of Kaluza and Klein. It also came with some sort of exciting possibilities that you could also get some of the other forces of nature like a U1 field out from the extra direction in some way. But these ideas of Kaluza and Klein, when you try to implement them, didn't quite work. And they didn't work because the standard model of particle physics is a very intricate theory with some very interesting features, which is that the matter content of the standard model is what we call chiral. It has a handedness to it. Okay, if you take a mirror image of the standard model matter content, you don't get back the standard model matter content. You get back another theory. And so by chiral, I mean you can take every particle, say massless, and look at as it moves, whether it's spinning in a right-handed way or a left-handed way, and the two are different states. And it turns out that you don't have a right-handed field for every left-handed field in the standard model, and in fact there is no right-handed neutrino, for example. Okay, so the matter content is chiral, and you could not accommodate this kind of chiral matter if you were going to try and execute the ideas of Kaluza and Klein. This was a no-go theorem which was made quite precise. So you had these extra dimensions, but well then you couldn't really get interesting gauge fields if you really tried to implement Kaluza and Klein's ideas. You couldn't get matter content under the resulting gauge fields which would arise of the chiral type. But actually it turned out in string theory you can evade this no-go theorem. And the reason for that actually is conceptually very simple. It turns out that the same kind of, I told you that all particles come out of excitations of the same underlying string, and in string theory you get the graviton, but you often get gauge fields in addition. For example, I mentioned E8 cross E8 or SO32, those are actually gauge groups of gauge fields. So you start in 10 dimensions with 10 dimensions and gravitons, etc., but also gauge fields. And when you have the gauge fields in addition, then you can circumvent the no-go theorems of Kaluza and Klein. You can get particle content which is actually remarkably close to the kind of grand unified theories people had tried to build going up from the standard model. Okay, so as you know, people tried to unify the interactions SU3 cross SU2 cross U1 into SU5, which could have proton decay that we looked for in India, or SO10, etc. And one of the very natural groups you get in string theory is E6 with a 27, which breaks down into SO10, with a 5 bar and 10 and so on, just of the kind that seemed very promising from the point of view of grand unification. So that was sort of rather good news. But now we come to the not so good news, which I mentioned to you, which is string theory has no free parameters, but its beautiful equations turn out to have many, many solutions. And the idea is that the coupling constants, as I was mentioning, that we see around us correspond to expectation values of fields. And as you look at different solutions or different vacua, we'll call these solutions vacua, you can think of these different solutions also as different phases. The reason for using that word is just as the same microscopic Hamiltonian, under different situations, different pressure, different overall energy can give rise to different phases of matter. Similarly, it's the same underlying fundamental equations whose solutions can be of many different types. So different vacua or different phases, it turns out the same underlying equations can have many, many different solutions. In these different solutions, the various properties are very different, can be. The cosmological properties can be very different. The particle spectrum and their interactions can be very different. And so you get out of the same underlying equations a diversity, a plethora of choices. In some cases the gauge group can be something like E6 or something akin to the standard model, other cases very different. Some cases chiral matter, other cases non-chiral matter, etc. And the cosmological constant, probably the most fundamental parameter governing the large-scale behavior of gravity, undoubtedly the most fundamental parameter, can take varying values. It can be less than 0, which is what we would have in anti-de Sitter space, as I mentioned, equal to 0, which is what we would have in flat space, or greater than 0. So you have a wide varying set of choices for these possible parameters. Now, why do such a large number of solutions? The underlying reason has to do with the fact that you start in 10 dimensions. The string theory leaves you little choice about, as I said. The structure is such. You have to have 10 dimensions. Then you try and make the extra 6 space dimensions small, but the equations allow you to make them small in many different ways. Okay? And all those different ways are consistent with the equations, so they should be allowed, and they give you different vacua with different properties. But in addition, it turns out there are other degrees of freedom. These are analogous to magnetic flux in electromagnetism. So you can turn these extra degrees of freedom on in the small directions, turn on extra magnetic fluxes, and that also contributes to the vast set of solutions. That adds a lot to the vast set of solutions you can construct. So because of all these different possibilities, you get a lot of solutions. How many? We're not very sure. There's good reason to believe, not 100%, but I think good reason to believe that the total number of solutions is finite, but it's astronomical, gigantonormous. I think, it's certainly of order 10 to the several hundreds. Okay, I think that is a reasonably precise estimate, I would say. Very large number. Widely varying values for the various constants of nature in all this, a kind of landscape which I've simplified here. I've only drawn one direction, but actually there are many, about 100 directions in field space. I've only drawn the cosmological constant. Other parameters vary, bigger value, bigger than 1, bigger than 0, less than 0, etc. A kind of landscape of possibilities here, a more artistic sketch as a sort of multi-dimensional set of possibilities. Many of them at least connected by tunneling or going over the barrier transitions, etc., and hopefully some of them being long-lived enough. Now, this gives rise, maybe I should say let me say the caveats first, which is the positive cosmological constant vacua are much more poorly understood in comparison to many of the ADS or flat space vacua. And this has to do with various reasons, including the fact that supersymmetry has to be broken necessarily, and especially we know from data, the data is not absolutely certain, but today the our leading understanding is that a small and positive cosmological constant is needed to explain the observational data, but that value is very, very small, 10 to the minus 30 in Planck units. It's especially challenging. It's challenging anyway to find positive cosmological constants, but in string theory, but especially very, very challenging to find such a small value of the cosmological constant. And so this is a question we need to face up to. There's a possibility which is much debated, hotly contested, hardly agreed upon, but which is an interesting possibility and goes back to the work of Steven Weinberg, which says in a very interesting way, the very fact that we have so many solutions might provide a kind of explanation for why the cosmological constant takes the small value it does. And this is called the anthropic principle, and Steve Weinberg was the first in a sense to propose it, I think, and he said, look, maybe the cosmological constant takes such a very small value in our universe, or maybe corner of the multiverse, if you want to say that. He didn't say that, I'm adding it in the context of current discussion. So in our universe, because galaxies would not form if it took a bigger value. If the cosmological constant takes a bigger value, then you have too much acceleration in the universe. Matter doesn't accrete, galaxies don't form. So you have to put in a little bit about the universe around us, and maybe that can explain why the cosmological constant is taking the value it does. Now, this is a very provocative idea. I started the talk by saying there's a hope of unification. that we can understand all the coupling constants of nature starting from first principles. Here I'm saying we have to resort to perhaps saying that we happen to live in a universe with some properties, maybe some of the constants or some of the values of the constants we observe take the values they do because of that. But this could be something that comes out because of the fact that there are so many solutions, and it seems quite hard to otherwise try and account for this very small value of the cosmological constant. But now at the end of the talk, I'm going into areas which are still very hotly being discussed and far from being well understood, including, as I said, both the existence of the positive cosmological constant vacuum and certainly any kind of understanding for why it might take a very small value. And in any case, we do know, even with these uncertainties, that there are a very large number of solutions, a very large number of vacua. And this raises many questions. How do we find a vacuum which corresponds to our universe, even if such a vacuum exists in string theory? What about the others? Who ordered the other vacua? Is there a multiverse? Are they connected? What is the correct conceptual setting in light of these vacua for cosmology? These are all open questions, and I think we need to address them as we go ahead. I'm out of time, so I'm not going to do justice for the other areas with which string theory is connected, which is a beautiful topic, but I have to show you this beautiful quote of Ashok Sen, which is one of my most favorite quotations, and it says, like the great epics, string theory also has many side stories. And what he is trying to say here is there is the main thread of string theory, as I've tried to put it to you, which is to try and provide a fundamental understanding of our world, a quantum mechanically consistent formulation, including gravity, but there are many other aspects, including the connections with mathematics, including the remarkable connections with condensed matter physics, which have had tremendous experimental consequences. The understanding of conformal field theories, which arose out of string theory, led to a tool which is routinely used in condensed matter physics. Topological quantum field theories, which arose out of string theory in an attempt to understand conformal field theories and their implementation in terms of Chern-Simons theory, is now a very important ingredient of condensed matter physics. The study of chaos, the fact that you can have new diagnostics of chaos, the out-of-time correlators, came out of string theory and the study of black holes. Black holes were found to saturate the chaos bound. That there is a chaos bound was formulated in the context of understanding black holes. And OTOX and these diagnostics of randomness, of chaotic behavior, are now a standard, are used all over the field in the study of quantum information, in the study of condensed matter physics. So, you know, this is a remarkable confluence of the ideas originating and connected to string theory, going back and connecting to other areas of physics. The side stories of this great, development connect to other great developments across physics and even mathematics. I think we'll hear more about it. The connections with mathematics are also spectacular. But I won't talk about all that because I'm out of time. So let me just end by saying to you all that here's a picture of a graphene flake where they're trying to implement the SYK model, whose behavior really reproduces in many ways the behavior of near-extremal black holes, including very fast-spinning black holes we see in our universe. So it's really quite remarkable. So I'll just end by saying string theory, I think, is a consistent theory of quantum gravity. We have lots and lots of evidence of that. That's the main point I wanted to bring across. And that such a consistent theory can be formulated combining gravity and quantum mechanics. To show that is, I think, string theory's greatest achievement to date. It has met many non-trivial checks, but we do not know if it describes nature yet. And this is the biggest question which remains. And of course, it's a very important question because ultimately we want to describe nature. We want to know, is there a quantum theory of gravity which can describe nature, explain what happened at the Big Bang, calculate for us from first principles the spectrum of small perturbations which we can compare against experiment. Okay, so formidable challenges remain. Hopefully future progress will allow a connect with nature to arise. One way or another, I put in my own view here, it seems likely to me that one way or another, the road to a final quantum theory of gravity describing nature will pass through string theory. If it doesn't lie in string theory, I think we will learn about how to get there through the developments that are ongoing in string theory. And with this beautiful picture of David Hockney, the world is not enough, this is the road, and you see glimpses of many landscapes as you go by in the progress of string theory. Thank you very much.
Okay, thank you, Sandeep, for an exhaustive and comprehensive survey. Any questions from the audience?
So how about for De Sitter universe? Is there any progress made on that?
We're very poor understanding comparatively of De Sitter spaces and a fundamental holographic description, although there's some progress. I don't know if Surat will talk about it. But comparatively, in terms of a microscopic understanding, here we had a very microscopic understanding of the hologram, that is some kind of Yang-Mills theory. We have a much, much poorer understanding in the De Sitter context. So we cannot as yet compute something like the properties of a black hole in De Sitter. Whether there is even a hologram, what form does it take, is something we don't fully understand. But the idea of holography is so general that I would say some version should be implemented in the context of De Sitter space. And one of the real areas where breakthroughs can occur is if there is a precise formulation of holography in the De Sitter context.
Okay, we have one interesting questions from online. Do you have any comments on the experimental discovery of supersymmetry and supergravity, given that their theoretical discovery was nearly 50 years ago?
Yeah. Well, I think perhaps the question is, look, we haven't seen supersymmetry at the LHC, and of course many of us hoped that was the case. I myself worked on that area, and it's not happened. What are we to make of that? Well, I mean, if you believe that there is supersymmetry, which string theory does not have leeway not to have in its fundamental formulation. There were two negatives, let me put it again. String theory requires supersymmetry in its fundamental formulation. Then you say, how is it that we are not seeing supersymmetry? And the idea is, of course, that supersymmetry is a broken symmetry. And we can't calculate, because we are doing not very well in terms of connecting string theory to the real world today, we can't calculate precisely where it's broken, at what energy scale it is broken. So I can't give you a prediction out of string theory today about what is the scale at which you would see the superpartners. So I think from the point of view of string theory, the answer would be we believe it's there at some high enough scale, and it's not been seen, but we can't give you any guidance of what collider to build to see it in terms of energy.
Yeah, elementary question, perhaps my confusion. You gave the correspondence of counting of the states for entropy. One end for the weak coupling you had the deep brain counting, and strong coupling you got the black hole entropy. Now, as far as calculation is concerned, varying the coupling constant is fine, it's a trick. But that would presumably mean that there exist states in string theory such that if the coupling were larger or smaller, they will either describe black hole or a collection of deep brains. Now, if the black holes actually exist, does it tell you that the coupling should be so and so?
No, so the kind
How
of...
am I supposed to, mathematically varying the coupling constant is different from physically realizing the variation. So this I will be able to connect.
No, that's exactly correct. So the kind of situations in which the calculations I was telling you about, where you vary the coupling constants, have been done, are situations where the string theory you're discussing allows for some fields to take continuously varying values. So you have a class of string compactifications. For example, you can take string theory and compactify it on a 6-dimensional torus. Now this does not fix the value of the dilaton, which determines G string. So you can say, look, I'm going to take string theory where G string is very small and take a system which has the lowest energy for this given set of charges and compute it microscopically. Now I take the system with the same charges, but when the dilaton has gotten a much bigger expectation value. So it's a different range of value for this field. There I will do the counting. And there you get the counting out of Bekenstein and Hawking, because the system has become a black hole. Now the question is, if you're getting agreement, should you have got agreement? Can you argue from first principles that theoretical consistency demands that the number does not change? Now here, the mathematically precise quantity which you can argue will not change is the index. Then you have to say, okay, I can compute the index microscopically because I can do anything microscopically. But on the gravity side, you have much less control. All you can compute is the Bekenstein-Hawking entropy. That's the total number. Why did the index have to agree with the total number? That was a loose point in the argument initially, but today, because of the work actually Ashok really, and then Dabholkar and Murthy and so on, for the kind of black holes I described, have really clarified this. You can argue if you have enough supersymmetry and you're say in 4 dimensions, then a black hole cannot carry, which has this much of supersymmetry, cannot carry any angular momentum. Now, fermion number can be thought of is -1 to the f, fermion number or its effects are tied to rotations by 2 pi. And the distinction between bosons and fermions you can see if you rotate by 2 pi. But if you can't have any angular momentum at all, you can then argue that states have to be invariant under a rotation of 2 pi, therefore must be all bosonic. So you say that at the other end, I'm also computing the index on the gravity side. I'm also computing the index, but I can tell you that there are only bosonic states. So therefore, degeneracy, NB plus NF is NB. And that's how the argument shows that you compute the index on both sides and you get agreement.
No, my question wasn't about the agreement between the two.
Oh, okay.
That I understood.
Oh, so sorry, I'm
Sorry.
I'm so sorry.
My question was, physically, how do you realize variation of the coupling? Because that will correspond to ground state being changed with respect to which you take expectation. It's a physical process, not mathematical.
You're
thing.
saying in the real world, how would you do it?
Real or, I mean, I'm not talking about real world in 4 or whatever dimensions.
Yeah,
That is
so
not a question right now.
the non-supersymmetric example I gave you, where you had a black hole which was heated up, there we did not use this argument of changing the coupling constant. We did not use this argument. We calculated in the same regime on both sides. In one side, it was a very, very difficult calculation. The microscopic calculation was very difficult, but conceptually very simple. For that reason, we could do it on the lattice. This is a heavy-duty quantum Monte Carlo runs. So we calculated in the same regime in 2 ways: gravity and heavy-duty quantum Monte Carlo, and it's bang on agreement up to 5 to 7%.
Okay, we'll have one question more. Yeah, go ahead.
Okay, I wanted to ask about, I mean, of course, it's clear that there is no clear-cut way of experimentally verifying this. But what might be the direction that one might go? Is it that one has to look at black holes in order to look for quantum effects in that? Or is it that one has to look at very small systems and, maybe the radial dependencies of gravity or whatever, something, or maybe magnetic monopoles? What is the likely direction in which experimentalists should try to look for evidences of...
Well, no, this is a very good question, and I'm sorry I cannot give you a very good answer, but I'll give you a more theoretically oriented answer, at least to begin with, which is, from the point of view of a string theory, the first thing you want to get right is the crude features of the universe we live in. So the fact that you are living in a universe which is smooth but with a small positive cosmological constant, you want to try and get something like this right. Because if you haven't gotten that right and you're trying to go after detailed properties, you're sort of missing the elephant for the forest for the jungle. So that's what I would say, but that doesn't help in terms of actually guiding for research. So I mean, I'm reluctant, people propose scenarios. They'll say, oh, maybe the large extra dimensions, go look for this, that, or the other. But I'm hesitant to do that because none of them is a proof or a test definitely of string theory. If the dimensions do happen to be large and you discover them, that would be great, you go to Stockholm. But if they're not large, you haven't ruled out string theory or something. So I'm sorry, we don't have the kind of tests that we could do numerically for the black hole to test string theory today.
The other question relates to you said that in the anti-de Sitter space, you have certain nice properties coming out. But do we live in an anti-de Sitter space?
No, we don't.
So now, is there something which is being done to show that it actually holds even in the space that we
Yeah, so that's right. That's another important point. And as I was trying to say, our understanding of the de Sitter space, the positive cosmological constants, is still nowhere near as good as that of anti-de Sitter space.
And a final question,
Yeah.
short one. Do you have any prediction on the dark matter sector?
Yeah, I mean, these are all great questions. These are all great questions, but we do poorly enough in dark energy that
That's really
that
bad. What
it's-
about dark matter? Because we have much better experimental evidence.
I mean, the one
that
thing-
either it is
Yeah.
dark matter or it is modified gravity.
Yeah.
So
I'll tell you,
light.
there are things which are predictions and there are things which are suggested, okay, and it's important to make the difference. And among suggestions, one thing which does come out of string compactifications is that you typically have axions in the system, okay? You typically have axions, in fact, you typically have quite a few of them. Now, this is not a proof. It's not as if I can tell you the compactification of string theory which corresponds to real world must have axiom, no. But if you ask generically among class of
But
compactification,
this idea of the axion was there even before string theory.
this idea of axion was there as a QCD axion
Yeah.
even before. But what string theory gives you is a wider range of parameters, both the f of the axion, it need not be a QCD axion, but it may couples, to electromagnetism through AFF dual. It need not have the parameters, the f of the axion, etc., that people needed for the QCD axion. So in terms of guidance, and people who are searching for axionic dark matter, they've certainly taken this to heart. It helps to build, a detection system which allows for a range of values rather than be very finely tuned on the QCD axion. Because you could implement that idea for dark matter without necessarily solving the strong CP problem itself.
Would a finite measurement of the neutron electric dipole moment help in that direction?
I wish I could say that, but I think it's a little far from where we understand the string
I'll ask
theory.
one last question from the online and then we'll stop, which is, what is the open question that you're most excited about?
The one I'm most excited about is trying to ask, well, I'd love to show one way or another where the de Sitter space really exists in string theory. And I myself worked, in trying to say that yes, it's quite likely, but the sort of definitive proof, if I can elaborate in the kind of constructions I was involved in, is the following. We say that because you have so many dials and knobs, you can work up to some approximation. But the proof that that is correct will only arise if you can compute to next order in terms of alpha prime, etc. corrections. And that is not so easy to do today because of Ramon fluxes, etc. involved, but maybe can be done. Alternatively, there are other constructions which have now been suggested for de Sitter space, and I think they can be explored. So one key question for me is, does de Sitter space exist in string theory? Yes or no? A sort of definitive check or test of the kind we have, or rather proof of the kind we have. The other would be then to try and understand string theory in de Sitter space, but more generally in cosmological backgrounds. Is extremely poorly understood, and I think that's really what I would love to do.
Great. Let's thank Sandeep again for a very nice talk. So we'll meet again in 20 minutes.
Sorry to go over.
Thank you.